Hello, welcome to Chapter 11, Part 3. In this last part of the lecture from this chapter, we will be looking at heat and the first law of thermodynamics. Let's start off this lecture with a little thought experiment. What happens if we were to place a hot block of metal against a cold block of metal? So here we have our hot block of metal on the left side, and remember what we mean by something that has a high temperature is that it has a lot of thermal energy, meaning the atoms inside of it are wiggling and vibrating vigorously, right, with a lot of speed and a lot of amplitude. On the other hand, a cold piece of metal, the atoms are not moving as much. So when we first place these two together, what happens here is at the point of contact, the atoms in the hot metal, which are vibrating more, bang into the cold atoms over here that are not vibrating as much. And this transfers energy because they start knocking against them and forcing them to start vibrating. So over time, we see that thermal energy is being transferred from the hot metal over here to the cold metal. And you can see as these cold metal atoms start wiggling and shaking more, they start knocking against the ones next to it. And over time, this whole cold piece of metal has now become warmed up in temperature because thermal energy has transferred from the hot metal to the cold. So this leads us to the concept of what physicists call heat. And heat is given the abbreviation for Q. Heat is thermal energy that's transferred from one object to another or between a system and its environment due to temperature differences. And the unit of heat is a joule because heat, remember, is thermal energy that's being transferred. So in this part of the lecture, we'll be dealing with the effects of transferring thermal energy into a system or removing it from a system. And again, this is called heat. Now, one of the properties of heat is that it can only move from a hot to a cold object. So this is a statistical result that when we take a hot object, remember on the average, the atoms in the hot object are moving faster than the atoms in a cooler object. So since these collisions between the atoms are elastic collisions, we can actually model this by this demonstration down here where it shows an atom here coming in from the left fast, collides with the red atom here, which is initially at rest. And notice what happens is the blue atom here transfers all of its energy to the red atom. And this is the result and consequence of an elastic collision. All right, a collision where they don't stick together, they bounce apart. So what we're seeing here is, this is just one example of one atom. But when we have an atom that moves fast colliding with one that moves slow or is not moving at all, we see a transfer of energy. So as a result, we always see a transfer of energy from the hotter object, where the atoms are moving faster, to the cooler object where they're moving slower. And in fact, this is part of what is called the second law of thermodynamics. We're not going to study the second law in much detail in this course, but this is one example where we will see some consequences or results from the second law of thermodynamics. It states that heat flows from hot to cold. Heat cannot spontaneously flow from cold to hot. So when we have a hot object transferring thermal energy to a cooler object, what happens if we just let this system keep running? Well, the two systems will, they'll transfer energy from hot to cold until the temperatures of these two systems is the same. So in other words, the hot object cools down because thermal energy is transferring to the cooler system. And then the cool system over here on the right is, of course, warming up because it's gaining thermal energy. So at some point, their two temperatures reach the same value. And this is called thermal equilibrium. Heat transfers from hotter object to cooler object until they reach the same temperature. Once this thermal equilibrium is achieved, there is no net thermal energy or heat transferred between the two systems. Any energy going to the right is offset on average by energy going to the left, and so they remain in thermal equilibrium. Now that we have a nice definition of heat, we can talk about what is called the first law of thermodynamics. And this is, the first law is one of the fundamental laws of physics. So there are two ways we can increase the thermal energy of a system. Let's say we've got a container of water here, and we'll stick a thermometer in it just to monitor its temperature and therefore its thermal energy. The first one, obviously, if we want to heat up this water, we can add heat. So we can place this container of water over a flame, and this diagram here indicates that we have heat. Remember, heat is Q. We have heat transferring from the hot flames, into the cooler water here. So we have heat flow going from the flame into the water system here. And as a result, you can see that the temperature of the water will obviously increase. So the first way to increase the thermal energy of a system is simply to add heat. And so the change in thermal energy, delta E thermal, of this system is equal to Q. And Q is the amount of heat in joules added to the water. But there's another way we can also increase the thermal energy. We can do work on the system. So if we take, for example, a paddle and stick it in the water and spin this paddle around really fast, you can think of this like a blender, all right? What's happening here is the paddle and the friction involved increases the water molecule speeds. Okay, this churning of the paddle and rubbing against the water, knocking against the water molecules is going to increase their speed, and that's going to increase the temperature of the water, as shown here with the thermometer. So that means by doing work on the water, we are increasing the thermal energy of the system. All right, so the second way to increase thermal energy is that the change in thermal energy here is equal to the work done on the system. And this looks very reminiscent of the work energy theorem that we talked about earlier in the course. Remember, when we did work on an object or a system, we increased the energy of that system. So we're seeing exactly that right here. We can combine our results from the last slide into a single formula that keeps track of these quantities, and this is called the first law of thermodynamics. So the first law of thermodynamics is really a statement of the conservation of energy principle. It says that the change in thermal energy of a system, delta E thermal, is equal to the sum of the work done on the system plus the heat added to the system. So W plus Q is the work done on the system plus any heat added to the system. So really, that's all this is. It's conservation of energy. When we do work or add heat to a system, it's going to change the thermal energy of the system by the exact same amount of joules. Both of these are measured in joules. The first law of thermodynamics there's a little bit more to it than at first glance, because all the quantities, delta E thermal, Q, the heat, and W, the work, can also be negative quantities. They don't have to be positive. So this is a diagram from your textbook, which at first is a little bit confusing, but basically what this shows is the system is inside this red box here, and outside of the system is the environment, whatever surrounds the system. So over here on the left, these are ways that we can add energy to our system. So these purple arrows going in show energy entering the system. And how do we do that? Well, there's two ways to do it. We can do work on the system. In other words, the work can be positive or greater than 0, or we can add heat to the system. In other words, Q would be a positive quantity or greater than 0. However, we can also take energy away from the system. That's over here on the right side. This is energy out. So see the purple arrow here representing energy leaving the system. This purple arrow represents energy leaving the system here. So how do we get energy to leave the system? We can have the work be negative. Now, what does that mean? Well, that occurs when work is done by the system. not on the system. So if the system does the work on its environment, then that's going to come at the expense of energy. It takes energy to do work. So the system will lose that energy. So that's energy leaving the system. And again, that is negative work in the formula. Likewise, we can take heat away from the system. For example, if we take our system here, whatever it is, let's say our system is a container full of gas or hot water or something like that. If we place this system on a big block of ice, well, then heat is going to flow from the system to the surroundings, right? Remember, heat always flows from hot to cold. So in this case, Q, which is the amount of heat, would be a negative quantity, meaning the heat is actually leaving the system. Let's look at one part of this a little bit more closely. How does work increase thermal energy? So in other words, when we do work on a system, why does that increase the thermal energy of the system? Well, one way to think of this is, let's take an example here where we have a canister full of gas. This is called a cylinder here, and in the cylinder we've got this piston here, all right, with a plunger, and we can push this this plunger down and compress the gas inside of this piston here. Okay, so if we apply a force here, all right, we're going to squeeze the gas down into a smaller volume here. Now, what's happening here when we do this, obviously we're doing work because we're pressing on this with a force over some distance. So remember, work is force times distance. But what we can think of is the individual gas molecules, when they strike the piston here that's being pushed down, they bounce off elastically. But if the piston is moving downward, that's you can think of the analogy is like taking a baseball bat and swinging at a ball, and all of a sudden you give that ball energy. So all of these atoms here that are striking this moving piston here are given extra velocity. In fact, if you do the analysis here, if the piston is moving down with velocity v sub p, an initial gas molecule here, or atom, bounces off. Let's say it comes in with a velocity v. It leaves with a velocity v plus 2 times the speed of the piston. So this gas molecule has gained kinetic energy, just like the baseball has here when he swings the bat. So this piston acts, like a bat that's hitting trillions and trillions of gas molecules every second, giving them extra energy, and this increases the thermal energy of the system here caused by the work done. And by the way, if this piston were to be pulled out instead of in other words, if we let this expanding gas push against this piston and move it upward, now what's happening is the opposite. The gas is doing work on its surroundings, and those gas molecules, as they strike the piston, they're going to actually slow down because the piston is moving away from them in this case. So the gas, by doing work on its surroundings, will lose kinetic energy. So remember, this work here can be positive or negative. Positive work is when work is done on the gas. Negative work is when work is done by the gas. So this is sort of summed up by the properties of or phenomena of compression of a gas versus expansion of a gas. So compressing a gas, meaning making it smaller, increases the gas's temperature, and this is work done on the system by the surroundings. So we just talked about the piston model there, where pushing this piston in to compress the gas increases the speed and therefore the energy and temperature of the gas. You can witness this if you ever pump up your bike tire with a hand pump like this. After pumping up the tire, basically you're forcing a piston down like this, all right, inside of this cylinder here. And by doing that, you're compressing the gas and forcing it to go into your bike tire. So if after you pump up your tire, feel the bottom of the pump here, near where the hose comes out, and you'll notice that the bottom of the pump has become quite warm or even hot, depending on how much work you did on that gas. Another example that occurs in nature is star formation. In this case, what's doing the work is gravity. Gravity compresses these gas clouds into a smaller and smaller region until it actually becomes hot enough for nuclear fusion to ignite. And this happens around 5 million kelvins. But this is how a new star is born. And this new star, again, it got its initial temperature to start its fusion reactions from work being done by the surroundings on the gas in this gas cloud. The other phenomena is the opposite. That is an expanding gas, and that decreases in temperature. So where a compressing gas gets hot, an expanding gas gets cold. And this is work that's done by the system on the surroundings. So again, with our piston in the cylinder here, if this piston is allowed to move upward by the gas doing work and pushing on it, then these gas molecules lose speed when they do that. Some examples of this, if you've ever played around with CO2 cartridges, these are sometimes used in pellet guns. They're also used in model cars or rockets. But after the CO2 is quickly let out of this compressed container here, you'll often see this thing frost up. It becomes so cold that ice actually forms on it. Another one that's fun that you can do at home is called a cloud in a bottle experiment. And I encourage you to Google cloud in a bottle experiment, and you'll see how you can do this quite easily using an empty water bottle. You'll compress this gas first, let it cool down for a few seconds, and then quickly let it expand. And when it expands, the gas cools down suddenly and actually condenses into vapor. You have to put a little water or rubbing alcohol inside the bottle to sort of form seeds for the cloud. Another one that you can do that's real simple and basic is if you blow on your hand, there's two ways to blow on your hand. You can keep your mouth open and blow on your hand like you do when you're checking how your breath is, right? If you have bad breath. So and when you do that, you'll feel very hot, warm air coming out of your lungs, all right, when your mouth is wide open. But then if you blow on your hand with your lips puckered, like she's doing here, you'll feel that the air blowing on your hand feels cool. So why is it warm in one case and cool on the other? Well, in this case, what's happening is by puckering your lips, the gas inside your body is at a higher pressure, and when it escapes, it is allowed to expand a little bit, and so it feels cooler. This is kind of a neat picture here. This is a fighter military aircraft that's breaking the sound barrier, basically. But what's happening here is the air flowing over the wings of the plane gets compressed, and then when it leaves the plane, it expands. And when it expands, it very quickly cools down. And when it does this, any water vapor in the air condenses and forms this vapor cloud around the plane. So let's finish this chapter off with 3 examples of how to use the first law of thermodynamics for a gas here, or for a system. So the first one says 500 joules of heat are transferred to a system. 200 joules of work is done on the system. What is the change in the system's thermal energy? So let's write the first law of thermodynamics. Delta E thermal is equal to work plus heat. Now, the work done on the system is positive, so it's 200 joules. Heat, Q, was added to the system, so that 500 joules is also positive, so we just add those together to get 700 joules of increased thermal energy in the system. Now, let's look at number 2. 500 joules of heat are again transferred to a system that does 300 joules of work. What is the change in the system's thermal energy? So again, let's start by writing the first law. Delta E thermal equals work done on the system plus heat added to the system. Well, in this case, the system is doing the work. The system is doing the work on its surroundings, so the work is negative 300 joules. The heat, though, is added to the system. It's transferred to the system. So the 500 joules here is positive, but we have minus 300 plus 500, which is, of course, 200 joules total energy, thermal energy increase of the system. Let's do one more. A system's thermal energy decreases by 400 joules, while the system does 300 joules of work. How much heat was added or removed from the system during this process? All right, so this one we have to really be careful with signs and moving things around in the formula and so forth. So as always, let's start by just stating the first law of thermodynamics as delta E thermal equals work done on the system plus heat added to the system. And we're solving for Q, right? The question is how much heat. So Q is equal to delta E thermal minus the work done on the system. All right, so we're just moving work to the other side. So now we have to put in our numbers here, but we have to be careful. It says the system's thermal energy decreased by 400 joules. So delta E thermal is negative 400 joules. Furthermore, the work is negative because the system did 300 joules of work. 300 joules of work was not done on the system. The system did work on its surroundings. So this W here in parentheses is minus 300. Now, we have to be careful, right? Because we have a minus here and we have another minus here. So, of course, those two minuses cancel each other. So we end up with negative 400 joules plus 300 joules. And that is a total heat, Q, of minus 100 joules. Now, what does that mean? Well, if the heat, Q, is negative, that means this amount of heat was removed from the system. So the answer is 100 joules of heat was removed from the system. So that is the end of this chapter. I will see you in the next chapter. Take care.